Hello everyone, class 12th topic is comparison of reactivity of haloalkanes and haloarenes towards nucleophilic substitution reaction. Yes, nucleophilic substitution reactions already we have done in previous videos when we were dealing with haloalkanes. What they were? Let's recall. And today we will compare out of haloalkane and haloarene which is fastly reactive toward nucleophilic substitution reaction. Haloalkanes are represented with general formula Rx and haloarenes are benzene ring and X. In both cases, X is negative, R is positive due to electronegativity difference. These electrons are shifting toward X. Same here, carbon is there, this is carbon, this is X is negative and carbon is positive. Now, if another nucleophile like Nu is representing nucleophile, obviously it is carrying a negative charge, and if it is replacing old nucleophile X negative, such reactions are known as nucleophilic substitution reactions. Like this. This is nucleophile, stronger nucleophile is replacing weak nucleophile. Such reactions are known as nucleophilic substitution reactions, which can happen with two mechanisms, SN1 and SN2. Now the topic is, out of haloalkane, this is haloalkane and haloarene, which can give these reactions fast? The answer is haloalkanes. Haloalkanes are faster toward nucleophilic substitution reaction, where haloarenes are least, or you can say less reactive toward nucleophilic substitution reactions. Note down, haloalkanes are more reactive than haloarenes toward nucleophilic substitution reaction. Now let's go for the reason. Why haloarenes are less reactive toward nucleophilic substitution reaction? There are 5 reasons for that. Reason number 1, resonance. Reason number 2, hybridization. Reason number 3, polarity. Reason number 4, instability of phenyl carbocation. And reason number 5, electronic repulsion. Let's discuss these 5 reasons due to which haloarenes are less reactive toward nucleophilic substitution reaction. Let's start with resonance one. For that, we should have a command on resonance. That concept already we have discussed in 11th class. Resonance, the movement of pi electrons. This is haloarene, and we know on X lone pairs are available. Now if I will draw its resonance, so the movement will be like this. This lone pair will go for bond formation, due to which these pi electrons will be further pushed. Between this X and this carbon, double bond will generate. Now because X is donating lone pairs for the bond formation, it will carry a positive charge, and these pi electrons are shifted to next carbon. So here I am drawing that one, and this carbon will get negative charge. Why? Because it is getting the extra electron of this carbon in the form of lone pair. Now next movement, from atom to bond and bond to atom. This will be the next movement. Let's complete it quickly. Here will be the double bond. Now here lone pairs will come with negative charge. This carbon will become negatively charged. Next movement, atom to bond and again bond to atom. These are resonating structures which I am drawing, in which we are watching the movement of pi electron over entire molecule. Now pi bond will come here. It will remain as it is. Next movement, atom to bond and these pi electrons will go back toward X. The next resonating structure will be this, and molecule will come in original position. Only the difference will be the position of pi bond. First molecule pi bond was here. Now in last molecule we can check pi bond is here. Now pi bond's positions are changed after movement. Now next movement will be again like this. Now this side movement will be there. First time clockwise, and next time anti-clockwise structures will be drawn, and this you will get. So this is resonance. Now such resonance is not possible in haloalkanes. For example, I am using this haloalkane. Such resonance is not possible because for resonance, pi electron should be there for the movement. But here we can watch all our sigma bonds, they will not move like pi. Pi movement is easy because pi electrons are perpendicular to the molecule. Their shifting is easy. One electron can jump from like this movement. This is available in pi bonds, but not in sigma bonds. So haloalkanes can't show this type of resonance, but haloarene. Now check, due to resonance, what is the problem? Between X and carbon, there is a double bond. And we know in nucleophilic substitution reaction, we have to break this bond. Like if I am going to show nucleophilic substitution reaction, so obviously first we need to break this X and carbon bond. But due to resonance, the X and carbon bond is getting double bond character, and we know double bonds are stronger. It's a strong bonding. Strong bonding, difficult to break. But in haloalkane, only single bond is there, easy to break. This is the first difference. In haloarene, between carbon and X, we are getting partial double bond character. We will call it partial double bond character, let me tell you, because it is not permanent. You can watch, in first structure, only single bond is there. Now next structures, 3 structures double bond, again single bond is generated. That's why we will call it partial double bond. So due to partial double bond between X and carbon, bonding is strong. So it is difficult to break. That's why haloarenes are less reactive toward nucleophilic substitution reaction as compared to haloalkanes, in which such cases are not available. Only single bond is there, and single bonds are easy to break. This is the first reason. Let's go for the second reason. Second reason was hybridization. Whose hybridization? Check. This is haloarene I have drawn, and this is haloalkane I have drawn. We are talking about hybridization of this carbon. In haloarene, the hybridization of this carbon is sp2, and in haloalkane, the hybridization of this carbon is sp3. Dear students, size of sp3 orbitals, this is sp3 orbitals, tetrahedral, and the size of sp2 orbitals, they have a difference. sp3 orbitals are bigger because they are made up of 4 orbitals, s and 3 p's. And sp2 orbitals are smaller because they are made up of only 3 orbitals, 1 s and 2 p. Now due to this size difference, because it is using bigger orbital for the bond formation with X, so this bond is lengthy bond. And we know lengthy bonds are weak. And this bond, because sp2 it is using for the bond formation with X, it will be a short bond. And we know short bonds are little stronger. So tell, which bond can be broken very easily? This one or this one? The answer will be this. Their bond lengths are also checked by X-ray diffraction methods, and this bond length was 169 picometer and this bond length was 177 picometer. So this bond was bigger and weak, so it can break easily during nucleophilic substitution reaction. But in haloarene, the bond is short, that's why difficult to break. That's why haloarenes are less reactive toward nucleophilic substitution reaction as compared to haloalkane. This is second reason. Let's go for the third reason now. Polarity. Whose polarity? Let's compare. This is haloarene and this is haloalkane. Now we know, right now I said this carbon is sp3 hybridized and this carbon is sp2 hybridized. One concept must be clear here. sp2 hybridized electronegativity. Electronegativity of sp2 carbons are more than sp3 carbons. The electronegativity of sp3 carbon is around 2.5, whereas in sp2 it is from 2.75 to 3.28. sp2 hybridized carbons are more electronegative. Reason? Because they contain more character of S. If you will find percentage of S here, so it will be 33.3%. And here if you will find, it is only 25%. And we know S orbitals can attract electron better. So that's why the electronegativity of sp2 carbons are more as compared to sp3. Now, how these electronegativities will affect here? Let's check. We know nucleophiles. Okay, wait for nucleophile. First check here. Because R is less electronegative, so it will shift its electron well toward X, due to which these R's will get higher positive charge. But here we know this carbon is little more electronegative, so it will shift these electrons toward X but lesser as compared to this R. So this carbon will get less positive charge. Again I am repeating the concept. This R is sp3 hybridized, so its electronegativity is very less. That's why it is shifting electrons toward X up to larger extent. That's why it is carrying large positive charge. But this carbon is sp2 hybridized. Its electronegativity is little large as compared to normal sp3 carbon. So it will donate electron to X but in lesser amount. That's why positive charge will come on this carbon, but that positive charge will be less. This effect is proved by their dipole moments. The dipole moment of chlorobenzene is 1.69 D and the dipole moment of RX is 1.86 D. And dipole moments are direct measurement of polarity. Means this molecule is more polar and this molecule is less polar. Now, you know nucleophile is going to attack on positive particle. This is more positive, this is less positive. So don't you think this attack will be difficult? And this attack will be easy. That's it. That's why haloalkanes are more reactive toward nucleophilic substitution reaction as compared to haloarene. This is the third reason. Polarity of RX bonds. They are more polar. Haloalkanes are more polar due to less electronegativity of R, and haloarenes are less polar due to more electronegativity of carbon. Let's go for the next reason. We know during nucleophilic substitution reaction, the bonds are breaking like this in SN1 mechanisms. So we are getting R positive carbocation, and from this side we will get phenyl carbocation. This is normal carbocation, this is phenyl carbocation. Out of normal carbocation, like normal means from haloalkane side you can get methyl carbocation, CS3 positive, or 1 degree carbocation or 2 degree carbocation or 3 degree carbocations you can get. And in this case, always you will get phenyl carbocation. Means if haloarene have to show nucleophilic substitution reaction, first it need to create phenyl carbocation which are highly unstable. If we compare these carbocations and phenyl carbocation, phenyl is highly unstable as compared to these carbocations. That's why RX are ready to produce carbocations and are ready to show nucleophilic substitution reactions. But haloarene will have little hesitation problem because it have to create phenyl carbocation and which is highly unstable. And we know reactions do not follow the unstable particles. Reaction wants stabilities. So they will always tend to go for stabilities, not for instabilities. So that's why haloarene is hesitate for nucleophilic substitution reaction, because in this reason we can understand haloalkane can create these carbocations which are quite stable as compared to phenyl carbocation. So this is the fourth reason that why haloarenes are not going to nucleophilic substitution reaction. And the last reason is electronic repulsion. Electronic repulsion. Haloarene, benzene ring, X. Now we know what are nucleophiles. Nucleophiles are negative particles and here it want to attack. But you can check, it's a benzene ring, lot of pi electrons are there. It's a X which have a negative charge, also have a lone pair. So don't you think these electrons, these lone pairs, these pi electrons, they are negatively charged particles, electrons they are, and this is also a negatively charged particle. So what problem will arise here? Repulsion problem, which we call electronic repulsion. Secondly, it is showing resonance, due to which overall we have a movement of a negative charge. That's why this whole molecule have a negative field around it, electronic field, due to which nucleus is not able to attack on this carbon, due to which problem? Repulsion problem. It is negatively charged particle around benzene ring, around haloarene we have a negative field. So that's why nucleophile is not ready to attack on a haloarene and nucleophilic substitution reaction will not happen easily. But in RX, we know alkanes are there, like this chain, this chain. Do we have pi electrons? No. Do we have resonance? No. So nucleophile can easily attack this carbon because it is not facing a repulsion problem from electrons, which we were facing in the problem of which we were facing in the case of haloarenes. That's it. These are the 5 reasons due to which haloarenes are not showing nucleophilic substitution reactions easily, but haloalkanes can. Thank you very much for watching the video.